All right. Last speaker of the morning, Nick Bohlsen from ANU, talking about classifying chaos and other stuff with topological data analysis.
Hello, everybody. I'm Nick. I think I've met most of you now because it's basically the penultimate talk of this. It's been a long 2 weeks. I'd like to thank Nathan for my sort of introduction. Oversold what we're going to do here, but such is life. So what I'm going to talk about today is we've been working for a little while now, for about a year, on developing applications of topological data analysis, which is a sort of series of mathematical tools designed to study the topology and geometry of data sets automatically. And we want to use these tools to study the topology, to study dynamical systems properly. And so we're looking mostly at physics examples. And today I'm going to talk about field lines, basically. So we're going to look at, I'll just skip the actual line. So I'll give a brief introduction. So the observation, though, is that stellar physics is, you don't need to actually read all the work. Stellar physics is obviously inherently geometric and very, very chaotic. So if we can provide tools that can characterize that chaos automatically, that is hypothetically useful, basically. We want to try to remove as much irritating science work where you spend 95% of your life looking at Poincare sections and reading things off as possible. Trying to avoid having to do that so that we can actually focus on design of the machine itself and on the actual physics analysis. Okay, and this is largely a problem because we can produce way more plasma configurations, simulations plasma configurations, than we could possibly reasonably identify and actually spend time looking at. I can make thousands of spec equilibria in a day. I can't really, well, assuming I can make it converge, but regardless, hypothetically, I can make a lot of them. But I can't reasonably look at thousands in a day. I want automated tools that can at least pull out interesting features of my simulations without me having to go and do it myself. Okay. And recent-ish, by recent, I mean, the past 25 years, in computational topology has given a series of tools for doing things of this type that look at the shape of data sets. Well, I'll make that notion cleaner in a second because data sets don't really have a shape. And has demonstrated their use in nonlinear dynamics. In fact, Kaczynski here, his work with Michel Lichowski, whose name I can never pronounce, is technically the basis for the relatively recent proof that you actually get chaos in the Lorentz map. So this computational topology stuff has not only been useful purely numerically, but it's also a core feature of computer-assisted proofs about nonlinear dynamics. Okay, and our aim is to do this for the extraction of topological features in plasma physics. Okay, so what I'm going to specifically focus on today is trying to automate a segmentation procedure. So if I show you a Poincare section, the first thing that the first thing that you immediately do in your head is segment all of the field lines into whether they are a large chaotic layer, invariant tori, or island chains. And that's an analysis that is blatantly obvious to a person when you look at the Poincare section. It is not blatantly obvious to a computer. So the question is, can we develop software that will automatically do that segmentation only from the information in the Poincare map? I want to use the same information that you yourself have when you look at the image and no more information. Obviously, we could use things like the converse cam theory, but that requires knowing the full orbit, or being able to compute the full orbit, not just knowing the Poincare map, and being able to actually compute these derivatives along the way. So you're bringing more information in when you do that. We want to use the same information that a person has. Some of this early work in related fields was a sort of artificial intelligence thing, and it was about trying to write computer programs that think like people. And so we want to try to work out how we can do this. Okay. So we're going to do this by looking at the fundamental observation we're going to make here is really simple. It's that I can distinguish the different classes purely by their topology, basically. So if I'm, say, looking at a field line that is on a island chain, what I know is that it'll be made of a series of disconnected loops. So what I'm going to go and look for is I'm going to count the number of connected components in my trajectory, and I'm going to count the number of holes in it. That gives me a measure of how loopy I am and how many connected components I am. And that will actually give me a good enough estimate. So for an invariant torus, I know that it will be a single connected component and a single loop. That is very measurable. For an island chain, I'll be looking for many connected components and many loops. For a large chaotic layer, I'm actually going to go looking for a single connected component, but many holes in it. So it's going to be full of loops, which is all the islands that are embedded in it. But that means that still gives me a well-defined criteria. One connected component and one hole is an invariant torus. One connected component, so many connected components and many holes is an island chain, and one connected component and many holes is a chaotic layer. There we go. There's my segmentation. Now we're just going to work out how do I actually compute from a finite list of points how many holes are in it, because that isn't super well defined. Because the problem is that intuitively I can ascribe, just looking at data sets, a notion of shape or topology to data. So here is the classic example. I have two data sets. One looks like a blob, and the other looks like a blob with a hole in it. Yeah. We want to detect the fact that there's a hole in the blob, yeah, and in a way that is preferably statistically robust and mathematically rigorous. So we want this to actually be a repeatable calculation that we can say actually write some theorems about. And this is what TDA, topological data analysis, seeks to do. But it's a problem if you think about this, because fundamentally, so what I'm going to do is try to describe here the topology of these data sets. But the issue is that at a pure fundamental level, these data sets are point clouds. It's not the only choice of data set you can do, but it's the one we'll worry about today. And point clouds inherently have basically trivial topology. They are made, if I have a finite list of points in a space, they are in a complete space. They are by definition a disconnected set of points, assuming they're all distinct. So they have the topology of a set of disconnected points, which is not very helpful. So I need to give them more structure than that. Conveniently, we can do that. And what we're going to do is take our data set and assign to it a family of simplicial complexes. So we're actually going to make a bunch of graphs out of it, fancy big graphs. And then those will have well-defined actual topology. They've technically come equipped with compact weak topology, such that we can actually compute the number of holes in each of the graphs. And if we can do this in a way, so I'll finish this little discussion in a second. This is going to be sort of run. So the first thing you might think to do, and the thing we're mostly going to do, is associate to my data set a graph, what we're going to call it, a Vietoris Rips complex, where basically I'm going to make an abstract simplicial complex. And I'm going to do this by looking at any list, so I've got n points, and for every set of points that is mutually within an epsilon distance of each other, I'm assuming I'm in some metric space here, that is within an epsilon distance of each other, I'm going to add a triangle or a hypertriangle whose vertexes are those points to my abstract complex. Some notes, this complex is definitely not embeddable in the space that the points live in, because, well, there will, at the end, if I make epsilon really, really, really big, every point is within epsilon of every other point. So if I have n points, there will eventually be an n-dimensional triangle in my complex, an n-dimensional tetrahedron. That doesn't really stop me. So this is technically an abstract complex, and it lives in some abstract space, but it's reasonably well behaved. And it has a couple of nice features. One, it is very, very computable. That's why I'm going to focus on this one. It's actually not the geometrically nicest choice for how to do this. There are better choices, but this is the most computable one. And the other advantage is it does let me gain some control over the scale at which I analyze my data set. So the underlying problem, so here's the first thing you could think to do if you want to do computational topology, is I just take my point cloud, I pick an epsilon, I construct this complex, and I compute the homology of that. I compute the topology of that complex, which we'll define a little bit later, a little bit better. You may note two problems with that idea. The biggest one is I have to choose epsilon. So here what I'm doing is I'm taking an epsilon and drawing technically what's called the shadow of the Vietoris Rips complex. It doesn't really matter. I'm embedding it back. I'm projecting it down back into the space. And depending on the epsilon, I get a different complex. And they're actually topologically different. So if I choose epsilon really, really small, basically none of the points ever get connected. So it still just looks like a whole bunch of disconnected points. If I choose epsilon really, really, really big, all the points get connected and it looks like a black blob. So now it just looks like one giant point. If I choose epsilon at a middling distance, I get to see interesting structures. So here this actually has a proper loop in it, in this version of the complex. And that loop is meant to be the real loop that's hiding in the data set, because a toy data set was made to have a loop in it. But so you'd ask the question of, well, how do I go about choosing epsilon? Because it's quite an ugly hyperparameter and there's no real a priori way to determine it. And the answer is you don't. What we're actually going to do instead is work through every epsilon. And I'm going to slowly increase epsilon. And as I do, my complex will get bigger and bigger. But it's actually always nested in itself. So the key mathematical feature that's hiding here is if I vary epsilon from 0 to infinity, I actually get a finite sequence of complexes associated to my data set, and they're all nested within each other, such that I have natural inclusion maps from one complex into the next. That's quite a useful feature. So once we have this list of complexes, we need to actually describe what I'm going to compute. And I've been saying I'm computing the topology. I'm lying about that. I'm going to compute topological invariant or homology, which I'm going to give a brief review on. I would hope some people would have seen a little bit of it. But it is the invariant that we usually are talking about when we say how many holes there are in something. So the homology is effectively a topological invariant that counts the number of n-dimensional holes in a space. And it does this by looking for loops in the space that are closed, but not the boundary of anything else. So the classic example is always a torus, where if I can draw a little green loop on the surface that is closed, so it has no, I'm talking about the outer loop here. It has no boundary, which is what it means to be closed, but it is the boundary of a piece of surface. So that's not a hole. But if I draw a loop around the actual loop of the donut, it is closed, it does close on itself, but because I'm only imagining the surface of the torus here, there's nothing inside the torus for it to be the boundary of. And this is what we claim to say actually detects a hole homologically, is I always look for these loops that are closed but not boundaries. We're going to formalize this as a set of abelian groups, but that's the idea. Some review. So the way we actually go about this is we're going to do what's called simplicial homology, which is a particular type. So that image with little loops drawn on surfaces is really a version of a slightly different version of homology. They're isomorphic up to some choices. Instead, we're going to use simplicial, which means I'm going to describe my loops, my sort of paths on my space. So my space is going to assume to be a simplicial complex. So it's an assembly of triangles. And my loops are really formal sums of my triangles, basically. So I can just make an abelian group by adding triangles. I'm free to do that in a formal way. What matters is that I need to do this in a way that sort of preserves the boundary behavior that I want. So the example here is I'm going to need to construct a particular operator that acts as a boundary on my little loop stack. So I can make my loops as sums, like I'm saying. So if sigma is a particular triangle, I just make formal sums over my sigmas in n dimensions. But one of the things I want is to be able to make boundary operators that take me from a n-dimensional formal sum to an n-1 dimensional formal sum to an n-2 dimensional formal sum. The same way that here I had a sort of 2-dimensional region and its boundary was a 1-dimensional region. I want some notion of boundary that takes me from a higher dimensional thing to something 1 dimension down and on and on and on and on and on. Okay, and that's reasonably easy to do. These are triangles. I literally do the boundary sort of the way you might think I do. So if I have a line, its boundary is the sum of the endpoints of the line. If I have a triangle, its boundary is the edges of the sum of the edges of the triangle. And if I have a sum of lines, which is what I mean by if I'm drawing the shading, that means I'm including the face, and I'm always with these little diagrams, I'm always thinking about the highest dimensional thing in the image. So for this set of triangles, there is no face. So I'm talking about the edges because it's still the highest dimensional thing in the image. Yeah. So here I mean the sum of 3 edges whose boundary is the sum of the boundaries of each of the edges, because it's defined to be a homomorphism, which is the sum of the boundaries of all of the individual edges, which becomes all of these dots. And a thing that was hiding here is my coefficients are Z2. So on Z2, 1 plus 1 is 0. So actually this whole thing is just 0. So the boundary of that little loop was 0. So we've now got a fact that loops have no boundary. That's what we were going for. And in fact, the core feature that we want is this following theorem. That something that is a boundary, so is in the image of the boundary map, will always be closed. So it will always also have 0 under this special version of the boundary map. Yeah. Cool. So the fundamental idea of homology then is I aim to construct a hole as something that is closed, so is mapped to 0 under this fancy boundary operation, but which isn't itself the boundary of anything else. Because I have this sequence of maps, I can make this as a little quotient group. So really all I'm looking for is the kernel, all the things that go to 0, quotient out all the things by the image of the boundary map the next dimension up. So anything that is an n-dimensional loop that goes to 0, that isn't the boundary of an n+1 dimensional loop will be something in my homology. And you might recognize that this is actually, because this is a quotient group, these are equivalence classes of loops. And that's a useful feature because it means I know if 2 loops represent the same whole. If they are members of the same equivalence class in the homology, they actually represent the same whole. The equivalence relation is just that you're differing by a boundary. I might draw a diagram of that. I'll draw the classic little diagram. Not sure what to rub off, and I really don't want to rub off the not complement from. I'm rubbing off the other side. Topological idea. Not how much time I have left.
12 minutes.
Okay. So the idea is the same in 2D. So if I have this loop here. Yeah. And I draw some other loop. What it means for these 2 loops to be different by a boundary is really that if you consider the region that they so if you consider the region that they are the boundary. So what I sort of mean is that I don't know how to describe this.
The blue is almost invisible.
Oh, sorry. Oh, don't worry about it. It's a minor technical thing. It doesn't matter. I'm just gonna not bother with it. Yeah. Whatever. But the point is that this gives me if you give me a space, a topological space, I can ascribe to it this set of abelian groups that correspond to counting the number of n-dimensional holes. Okay. So what I now have is I have a point cloud. I can associate to that point cloud a series of simplicial complexes. I can then associate to those simplicial complexes a family of abelian groups. Okay. We now want to learn something about the abelian groups. And this is where the little observation from earlier that I have inclusion maps between my complexes is really useful. And this is because of a little theorem, which says that if I have a map between 2 spaces, 2 topological spaces, a continuous map between 2 topological spaces, which my inclusion maps by construction automatically are, then I will actually generate a map between the homologies as well. So for space X, if I have some map psi onto another space Y, then the homology of X will be able to be equipped with a map psi star, which is a homomorphism, between the homology of X and the homology of Y. Why do I want to do this? The idea then is that, I don't know how they're useful slogans. Yeah, it'll be fine. The idea is that I can actually look at how the topology of so I have a series of complexes whose topology changes as I keep applying these inclusion maps that take me down the sequence. And actually, I can look at exactly how their topology changes by looking at the induced maps under inclusion on the homology. So if a class is in a kernel of one of these induced maps under inclusion and homology, then actually that means that when I added an edge, I killed a hole. So if I say, imagine I've got a collection of dots. So here's a simplicial complex. Okay. It's made of, what was it, 5 dots, series of lines and a triangle. This will have, so the 0 homology always counts the number of connected components. So the 0 homology for this complex was going to be 2 copies of Z2. Yeah, it's got 2 connected components, this one and that one. The one's just a dot. Yeah. And in my next stage in my iteration, I'm going to add an edge. The edge I'm going to add is that one. My new complex has 1 less connected component because I've just connected this dot to that one. And the way that's seen in the topological data, in the homological data, is that in the induced map under inclusion, there will be an element of this homology group will be in the code. It'll get killed because the new homology group is just that big. So I've killed a class. And we can similarly ask the same thing. If I have classes that aren't in the image of my previous homology group, I know that I've created a new topological feature. So perhaps I would see if I was to add another edge, I might be able to create a hole. And I would see that by looking in the one homology and seeing that I've created a class. Does that remotely follow? The trick then is that once I know I can do that, I can run through this sequence and track how my topology changes over time and make a little diagram that tells me the homology in all the different dimensions. So here we have a point cloud, and we're going and slowly adding, credit to Robert Grice for this diagram. And we're going and slowly adding triangles over time in order, in size order, and drawing the homology. So these top section, this is all the zero homology classes. So it starts out as with a lot of homology classes because I initially start with a connected component for every point. And at the end, it's all connected together. So there's only one homology class. And so these black bars are indicating the lifetime of a topological feature. And when they stop is when that topological feature gets annihilated. It's when there's a class in the kernel of one of my maps under inclusion. And there's always one, so in this case, they slowly die as my point cloud gets more and more and more connected. And there's always one class that lives forever, corresponding to the fact that the whole structure is connected at the end. The section below the little gray line is the first homology. So this is the actual loops in the space. And we see that, yeah, about here, there is a loop created. The loop is that loop there. This little 4-point loop, that's the one that's been created. And that's why we've got a class here that eventually dies when this edge gets added. So there's an edge that gets added to cross that rectangle and, well, it's a polygon. And that edge is what kills that class. So we get a death time. And the whole idea, the underlying point of topological data analysis then, is that I can compute this and identify topological features from this little diagram, or really from the list of birth and death times, which is equivalent. And if things live for a long time, they're seen as a statistically significant topological feature. So the advantage of this whole procedure is that up to that measure of statistical significance by your sort of length of your bar, this is actually statistically robust. If I fiddle with the points a little bit, the persistent homology doesn't change much. I might create a whole bunch of really, really, really tiny bars, but I can consider that a small change in the overall persistent homology. Okay. So specifically, yes, the homology of the Vietoro's rich complex will change as I vary epsilon. And so classes will either be born or die at some diameter epsilon. And the set of pairs is what I'm going to call the persistent homology. The thing I'm going to actually go and plot here today in what follows is a slightly unusual visualization in the literature. The standard visualization is a scatter plot of death and birth times. And yeah, you make your measure of statistical significance the total lifetime of each bar. I'm not going to do that. Instead, I'm going to use as my measure of statistical significance the ratio of death time to birth time. This happens to be better for point clouds with structures on many scales, which our fractally field lines will. So I'm going with that choice because it's better for things with multiple fractal scale. So here's an example where I've got a loop made of 6 little loops. And what I'm looking for is to have 6 classes that look like, and this is sort of meant to be a toy model from Magnet Island. And I'm looking to see structures that look like these loops in my data set. And so if I plot, yeah, the death radius on the birth radius against the death radius, I'm plotting against the death radius because the death radius is a rough estimate of the size of the geometric size of a topological feature. So this, putting it like this, I have this in size order. So it's scale separated. And we see one point up here corresponding to the fact that the whole cluster is organized in a big loop. So there is a hole in this data set right in the center of it. Yep, and that corresponds to this dot here. The other 5 dots, the other 6 dots, yeah, they're the little individual loops. Okay. The concept then for automated point classification is you take a point, run its orbit for some amount of time, That gives me a list of, well, a cloud of points on the Poincare section. I then compute the systemology of this point cloud as a Vietors root systemology. I then want to work out a family of criteria based on that systemology that will let me answer this question of, is it by doing that same classification of how many connected components am I, how many holes are in me, so that I can work out exactly which type of field line I'm looking at. Up to some dodginess. Yeah, note that this is currently very non-rigorous. Okay, and as a test, I'm going to use the world's lamest toy model for tokamak. It's made of an infinite line current and a circle. Why? It's so computable. I like this model because you can write the exact field in the elliptic integrals in about 5 minutes and implement it in about 2 minutes more, and it's good enough for what I want. You get chaos, if you're wondering. You just move. So you get, this is perfectly integrable if you put the current right in the center of the circle. It's not if you just displace it by a little bit. So I'm going to displace it by a little bit. In fact, it's half a percent of the radius of the machine is enough to generate pretty enormous chaos in the island chain. That's what that image from right at the start of my field, my whole field came from. It's this model. Okay, so here's a cam torus. An orbit, well, it's not really a cam torus, but it's an orbit on a, it's actually just an invariant torus. It's really a nested flux image, but whatever, it's just put a cam torus in the file. And you see roughly what you might expect. So here I'm looking at the one homology, I'm looking at the loops here. And there is one non-trivial loop in it, which makes sense. It's a giant loop. That's a good sign that this is remotely working the way I would want. That I get one big dot corresponding to the fact that it's a big circle, and pretty much just tiny bits of little noise. There will always be little noise. It's a statistical procedure. Let's look at an island chain instead. So for an island chain, here we still get this, we get a lot more interesting structure here. So this class, that one here, that's actually the same as the previous one. So all of the things we're going to look at will have a version of that dot furthest on the right. It's a really important dot. It corresponds to the fact that these actually do lap around the machine. So these are, every field line I'm going to draw has roughly a circular shape because they have to fit inside the effective image of the tokamak. But the height of this point, sorry, how high that point is will change over time. So here it's enormous, it's at 60. Now it's about 2. That's indicative of the fact that we've now got big gaps because I'm no longer a single connected thing. If I'm a single connected thing, that point is going to be really, really, really high. When it's really low, I'm not connected. So instead I get, yeah, this point's now 2. Instead, and I also get a couple of other interesting things. I get 5 little dots here, all at large scales. They're the actual major part of the island. So obviously, I've really hit a minor resonance on a major island chain, but when I was fiddling with the data, so that's getting the these major islands. You don't see the 6th one because this one's really, really, really close to the center and ends up super smushed. It's an unbelievably elongated little island there that's almost just a line. That's just because of the way this sort of dodgy spherical tokamak is made. And we get a couple of other ones here that correspond to the fact that each of these is a little loop, because this is really quite a high order island chain. And there's then some noise. And for a stochastic layer, so here's a proper big chaotic layer. Yes, I'll fluctuate back and forth between calling it stochastic and chaotic. For a chaotic layer, we again see that last class, the one furthest to the right, is really big again, because this layer is now connected. So this immediately gives me a simple criterion to work out if I am a full loop. I'm going to look at that furthest to the right class, and I'm going to ask how big is what is its death on birth ratio. That's a quantity I'm going to call the enclosure. It's sort of a measure of how much it encloses things. Yeah. And if I go and actually plot it as a function of initial radius, so I've taken a run of 150 initial conditions on the inboard side of the machine. I've run them for a couple of thousand lines. I've computed the homology, and I've then pulled the enclosure value of each of the initial conditions. We see this sort of nice structure where it's high over here because all the field lines right at the start this is sort of like a giant dipole field. So all the ones right near the middle of the machine actually are gigantic closed loops. They actually behave really well. And as we go down, it then sort of bounces up and down. It bounces up when I hit something chaotic, and it bounces down when I hit another. So we get this nice sort of 2-level function And so I can just say, great, I've got a discriminator. I'm just going to draw a horizontal line through it and say anything above that, I'm going to declare to be an island. Anything below it, I'm going to declare to be not an island. And that gives us this coloring here automatically. And if you actually look at this, it's done a pretty good job. So all the sort of nested flux surfaces, although most of these I think are actually very, very fine stochastic layers, have been pulled. The really big chaotic layers have all been identified, and we seem to be hitting the islands. The only fiddliness starts to happen right at the very, very boundary, but I don't really care about that. Does that diagram make sense, people?
So in the diagram, are the closed flux surfaces the same color as the stochastic layer?
For now, because that's the way this currently works, at least for this particular check. Yeah. I'm going to go and check something quickly. So one of the other pieces of information that I have in the epistemology is the actual number of connected components. I can pull that. And for the things that are detected as islands, that is the toroidal mode number. So I can, because it's just how many actual islands there are, at least if I put some threshold and say I want how many, if I put some statistical significance on what it means to be an island. So I can pull the toroidal mode number. I also know the Q profile, at least for the unperturbed configuration, so I can compute the effective colloidal mode number, and I can go and check if my islands are being detected in the right spot, in that I can go and check if they're on surfaces of rational Q. And there, roughly. It's pretty good. So obviously so I've run down, I've pulled some stuff from a fiery tree at low water, and I'm checking if my islands, which are the little blue bits, are occurring around surfaces of rational Q, and they do. Good. Okay. I'll talk a little bit about separating out nested flux surfaces now. So this is still preliminary. We're pretty sure we can do it. The details are a bit subtle, so I don't really want to talk about them. It involves basically noticing that. So I think I've actually only hit one true invariant torus in this scan. This is a really chaotic configuration that is mostly very thin stochastic layers separated by cam tori in the core. So these flux surfaces aren't really super purely nested. So I've actually only hit sort of one right in the core. That's definitely a proper invariant circle. The others are very, very, very thin chaotic layers. And we can separate them, at least this has been done automatically here, by looking sort of at, I'd have to give the full discussion's a bit subtle, but what I sort of go looking for is this. So the note, I go looking for the size of this sort of blobby region. For a perfect cam torus, this is all, like I can provide the data if people are interested, but this blobby region full of noise basically always ends a bit before 10 to the negative 2. For things that are slightly thicker, so things that are really thin chaotic layers, this starts to smear out a lot. So I can sort of put a criterion on how many dots are there after a vertical line I draw here and use that to roughly distinguish. It's not perfect. That's a generically hard problem, separating a thin chaotic layer from an actual torus. And from a physics perspective, I don't think it really matters because they have basically the same, as far as I understand, they should have very similar transport properties because they're still opposing radial transport. But yeah, so I'm not sure it matters. I would like to be able to do it, but yeah. For now, we were really just trying to see, can I get the islands properly? There are some problems. I have to pick the different thresholds by hand. I can do the very last one, the cam torus one, not by hand. I'm not going to discuss the details on it. If you're interested, ask me later. We do have to run quite a lot of field lines. So I did the maths. This is probably computationally comparable to the talk from yesterday. We're running fewer field lines, but for longer. So I only run about 100 configurations, but I have to run them for 1 to 2,000 iterations. And computing the actual epistemology, at least with the standout, the main software, RIPSA, is very slow. We here at Applied Topology at the ANU think RIPSA is probably not doing things optimally. And Koyama, one of my colleagues, has developed a vastly faster method that can probably make that not so much of an obstacle. I did these with RIPSA because it's the standard, but we do have better ways of computing this. But yes, conclusion. So we've seen that we definitely can get the actual islands automatically, just from the information in the Poincare section, with nothing else needed. But some problems. I've only tested it for fairly dense point clouds. I'm not sure exactly what is the minimum number of points that you need. Yeah. And I haven't tested for a real tokamak field or a real stellar or equilibrium. This is a toy configuration. Yeah, it was just as a test problem. But main conclusion is this is actually probably, as far as we know, the first practical application in TDA in a remotely plasma physics context. We're hoping that more will follow. Things, and people want to talk about future. Okay, whatever. Great. Okay, cool. Questions?
Anyone got questions? Stuart?
Great talk. Thank you very much. On your second bullet here,
Mhm.
no information on the points is required, but you have that information.
Yeah, I know.
And it strikes me that, you know, the connectedness, that this point gets mapped to that point. That strikes me as being very valuable information.
It probably is,
So
yeah.
I was actually going to kind of say, aren't you throwing away a lot of information?
Yeah, probably. I would, yes. We wanted to see if we could, not really whether we should.
Yeah. The data set comes with more information. I just thought, how can that be? Yeah. Anyway,
So there are reasons you would probably not always want it. Like, it's good if you can use the more information. It probably would be better. But we wanted to see, could we like just very simply reproduce the segmentation that a person does? And obviously a human doesn't need the order. So the order clearly can't be required. If you can do it without the order, it cannot be absolutely required. It may be more efficient with it. I suspect that. But yeah.
Yeah, is there a notion of convergence for homology? So it's like as you keep taking more points of your trajectory?
There is. So this subject developed from partly work of Vanessa Robbins and James Meese on largely trying to do manifold identification from finite point sets. So if I imagine I've got some manifold that I've been able to take a finite sample from, the question was, can you work out what the manifold was from only the finite sample and do that rigorously? The answer turns out to be yes, but you need to, it depends strong, and like you really can do it in a way that does converge correctly. So where your position homology will converge correctly to the homology of the thing you're sampling from, but only if you've sampled correctly. So the way in which you sample the space is very important, because if I have clusters that form not due to the actual structure of the space I'm sampling from, but just due to my sampling, they'll be detected as extra connected components that shouldn't be there. So you have to be quite careful. There are some rigorous theorems that are about, if I assume that my points have been sampled with sufficiently close to each other and with some restrictions on sort of how tightly curved the space you're pulling from is, you can guarantee that the position homology will correctly reproduce the actual homology of the space, but there's strong conditions that are needed. I don't think they're realistic, to be honest.
Do you know how they relate to the dynamics? I would say that the sampling that you get on KM torus is actually very good. Like it fills in very evenly, and you very well could apply it on your tori islands directly.
Yeah, so we suspect that does work in this case. For chaotic layers, it's complicated and really bad. So we were pretty sure that it works really well for KM toruses and probably for islands. For anything that's quasi-periodic and ergodic, I don't think it works as well for actual chaotic orbits, and it's because the chaotic orbits get stuck near invariant toruses and stuck orbiting island chains for a long time. When they get stuck doing that, so if they get sort of stuck in the island forest, they oversample around the boundary of an island or next to an invariant torus. So you don't get an entirely accurate representation of what the whole surface was. So I have some data about this that you can look at if you want. But yeah, we're not super happy with the way exactly it samples for just the chaotic orbits running a fat fractal region. It oversamples unless you take really, really, really long times. Yeah.
I mean, that sounds like it could be the signal that you're not.
Yeah, you possibly could use that as a discriminator. I'm not certain though.
If you go back to, I think when you were showing the green line to represent the next to the
Yeah.
surface, Is there also some green particles on like this inner?
Yeah, there is. Those have also been worked out. They actually are invariant circles.
Oh.
So they actually should be there. Yeah. This is because of the way this configuration works. Near the near to the current in the center, you do get closure of the lines again. It sort of becomes integrable right at the edge. It's not, again, it's sort of like a dipole field at infinity, so it's not really realistic, but and dipole fields do these gigantic, long, sort of spherically Tokamak loops. So yeah.
So when you go to like, you said you're hoping to do with like an actual talk.
Yeah.
Besides the fact that you have to do things by hand, how difficult is it to like convert this? To
Not at all. It was just more annoying to do. But it's like all I really require is the actual list of points. It doesn't matter where you get them from. If you can provide me the list of points in real space coordinates. So the one thing that is needed, I need a metric. Here I have the ability to just use because these are in real space coordinates, I can just use the actual Euclidean metric on the space. But that is information that I require. Now you can always just equip your space. Well, for most all of our spaces, you can just equip them with one, but that's not necessarily geometrically robust. So we get what I mean by that. So if I was given the coordinates in very ugly sort of straight field line coordinates, it probably isn't right, I would argue. I would say that if you were to just equip that space with the Euclidean metric or something, you're not getting the correct behavior. Maybe you can do a sort of geodesic distance on the sort of imagined flux surfaces, but I'm a bit about that.
And talking about different metrics, I'm not sure if the Euclidean metric is the best thing because
it may not be.
Your field lines on the inside, like inside of your dipole, or even like in a tokamak, are much denser on one side, and so start getting groups much closer than anything on the far side of it. Could you maybe equip it with a nicer metric that
You can equip it with any metric you want, but it becomes a matter of actual sort of data analyst's choice, which is where we don't like having to make unnecessary choices. It would probably be better, and you probably could improve it if you're willing to do that, but you have to make that choice.
Yeah, I was gonna make a comment on that, is that magnetic field line flow is not area preserving, it's flux preserving. So your choice of distance, Chris was commenting, probably should be flux. Anyway, yeah, just a comment. Yeah.
That would probably also work, yes. I do agree with that.
From the information that you get from the simplex when you identify the elements, can you use that information to compute the area covered by the element?
So yes, sort of. One of the things we can actually do is pull actual representatives. So what I'll do this on the board. So the classes we're detecting are actually little formal sums of simplexes, but they actually, what that means is they're little, all the classes that correspond to loops are actual little connected lines if you have a simplex together. So I can go and work, one of the things the software that some of our tools can do takes a systemology class and will actually work out explicit representatives for it. So you can actually get an actual circle that is an actual loop in your point cloud that is actually closed, but not the boundary of the block. So normally this should be basically running along the outside of the block, outside of your island, which you could then go and use to pull like sort of bounding circles for all your island. The challenge is in getting it to pull the thing that is sort of the convex hull. So we right on the interior line. I think it is possible, but you need to, like, what I mean is, here's my region. I'm talking about the interior of this annular C-shape thing. When I go and pull my software, I will get a loop that is closed but not the boundary. So that could be, say, this loop. That doesn't really work. The problem is it's not guaranteed to be this nice inner one, at least not immediately. You can probably optimize towards that. So we can definitely get a single representative in the class. Finding the representative where I would argue the right you want is the representative with smallest length. I'm not certain that's exactly what you want, but it would be my first thought. I haven't really tested this yet. But trying to work out, can I find any other loop homologous to the one that it's given me? that has the littlest possible length is the question you need to ask if you want to actually get bounding circles, which is something we have been thinking about. Have we worked out ways to do bounding circles?
I actually have one. I was only looking at these Poincare type methods. You're always doing Poincare section from, phi equals 0 around phi equals 0. But in doing that, in introducing that field line, you're also getting data everywhere along the way.
Yeah.
Which in theory, you can also imagine a second set of Poincare sections from the half period to half period. Is there any way to make use of that?
I don't think so, because I think by continuity arguments, they're basically always topologically conjugate to whichever one you started with. So I don't think you really gain more information.
I feel like in the sense of being able to say, like, do fewer transits by using intermediate points and mapping them back to the equivalent. That makes sense.
Maybe you could do that. We definitely could do the actual class. So this classification doesn't really have to be just on the Poincare section. I want to do it on the Poincare section, but you could do the same thing by asking what actually is just taking my field line and asking the same question. I could treat all the points on my field line as a point cloud in 3D space, and I could ask what manifold does it do by the same trick. So I could ask, is this forming a torus? The problem I would have with that is that you need a lot of loops to get close to reasonably covering a surface. So I would think you'd struggle to uniformly explore. It's also, the computation is a bit harder. So this computation is fast. At least the new version of this is fast if you only want the 0th and 1st homology. Getting the 2nd homology, so detecting voids, is hard. Kiriyama's new method, we think, is faster than the existing, but it will still be slow. It is like voids are hard to compute.
Do you have an asymptotic cost? Like, what is it?
For RIPSA, it's complicated. It technically depends upon the way the points are arranged. But yeah, for the old way RIPSA does this is like n cubed or n to the 4th or something in the number of points. Kiriyama's is, I think,
like your epsilon, because you're varying epsilon too, so there must be some discretization happening.
no, you get all the epsilons. So it's just, I just mean in the number of points you have to get the whole position homology across epsilon from 0 to infinity is roughly n to the 4 for RIPSA. Kiriyama's method, I think, is n to the squared roughly. I think his version for doing 2 homology will be n cubed, but it won't be, like, it's n cubed asymptotically, but I don't think it'll actually be practically n cubed, because to do n squared well, he also needed some very clever tricks that were very specific to 2D Euclidean space that lets you do n squared, but also have the coefficient in front of the n squared be really, really little. I think in n cubed, not only does it scale as n cubed, but the coefficient will be big. So it'll start, even with small numbers of points, it's going to be really hard to do 2 homology. Yeah. RIPSA is really, really slow, I will note. It's very general, but the n to the 4 is because they want to do it on a completely abstract metric space. So all you need to give RIPSA is the actual distance matrix between your points. And that, whereas the others need, the newer methods need specifically properties of Euclidean spaces. So if you want to do this on a totally arbitrary abstract metric space, you do need at least n to the 4. If with really ugly point alignments can take even longer than that.
So I just want to say, a couple of days ago, in recognition of Nick's undergraduate coursework and also his research work, Nick was awarded a university medal. So that's extremely rare. So congratulations, Nick. So I think that's wonderful.
Thank you. I think we should let people go to lunch now.
Back at 2 o'clock.